Module 5, Lecture B, Advanced Pipelines. By the end of this lecture, you will be able to optimize tf.data pipelines using caching, interleave, and parallelism settings for large data sets, configure input pipelines that work efficiently with distributed training strategies, and diagnose and resolve common tf.data performance issues, such as slow startup or CPU bottlenecks. Interleave and cache. Efficient file interleaving. Efficient file interleaving is a way of reading from many data files so that both the CPU and the storage system stay busy without being overloaded. In large machine learning tasks, datasets are split into many small files, and reading them one at a time can cause delays when a particular file is slow. Interleaving instead opens several files at once and switches between them to keep data flowing steadily. This is especially important with networked or cloud storage, where file access speed can vary because it helps maintain a consistent stream of batches to the training loop. To use interleaving effectively, you need to choose how many files to read at once and how much data to prefetch from each. If you read too few files, slow reads can stall the pipeline, but reading too many adds overhead and can overload the storage system. The optimal level of parallelism depends on your environment. Local solid-state drives usually support more concurrent reads than network or cloud storage, which may require more moderate parallelism to avoid throttling. The goal is to interleave just enough files to keep your compute resources busy without causing slowdowns in the storage layer. Efficient file interleaving shapes how you shard and organize your dataset. Very small files create too much metadata overhead, while very large files make it hard to balance the load across workers. A good compromise is to use medium-sized shards that each contain many examples and can yield multiple batches. By interleaving these shards across training workers, you improve both hardware utilization and data diversity in each batch. When done well, this turns the file system from a bottleneck into a scalable parallel resource for training. Python code. Efficient file interleaving. This script shows how to efficiently interleave data from multiple files. It compares a standard sequential data pipeline with an interleaved pipeline built using the TensorFlow data API. The goal is to highlight how interleaving can improve data throughput. The focus is on input pipeline performance rather than on the details of model training. The line that begins with an exclamation mark is a shell command used to install TensorFlow version 2.20.0. It is typically run in a Jupyter notebook or similar environment. The purpose is to make sure that this exact TensorFlow version is available so the script can run correctly. This helps maintain compatibility with the code that depends on TensorFlow's features and functions. We begin by importing several key modules for our script. The operating system module lets us work with the file system, and the time module provides tools for handling time-related tasks. We also use the temporary file module to create short-lived files and directories for data that does not need to be saved permanently. Finally, we import TensorFlow, a machine learning and data processing library that will be central for building and managing our data pipelines. We use TensorFlow's random module to set a global random seed so that any random operations give the same results every time the code runs. This is important for reproducibility when experiments or models depend on random initialization or sampling. By fixing the seed to a specific value, such as 7, we ensure the sequence of random numbers is consistent across runs. This consistency allows for reliable comparisons, easier debugging, and more trustworthy experimental results. We start by printing the version of TensorFlow that is currently in use. Knowing the exact version helps confirm that your environment matches any requirements or instructions you are following. It is also important for debugging because different TensorFlow versions can change features or behavior. Checking the version makes it easier to identify and resolve compatibility issues. We begin by creating a temporary directory using the standard library's tools, which gives us a workspace for our small dataset. We add a specific prefix to the directory name so it is easy to recognize. This temporary setup is helpful because it keeps short-lived files organized and prevents them from cluttering the main file system once we are done. This function creates small text files for later use. It takes a file location, a number of lines to write, and a delay factor. Using TensorFlow's file tools for broad file system support, it opens the file in write mode and loops for the given number of lines. In each loop, it writes a line containing the delay factor, a comma, and the current line index. These lines are later used to simulate different processing delays in downstream operations. We configure the setup to create 4 separate text files, each containing 20 lines. These files are prepared specifically so they can later be used to simulate different processing delays. By working with multiple files that behave differently, we can more clearly demonstrate and compare how various data pipeline strategies handle efficiency under different conditions. We begin by setting up a list to store the paths of all files in our dataset. A loop runs for the desired number of files, and in each iteration, we build a file path by combining a base directory with a file name that includes the current index. Using this path, we create a text file with a fixed number of lines and assign a unique delay factor to each file based on its index. After each file is created, its path is added to the list so we can easily access and manage all files later when constructing our datasets. The code turns a list of file paths into a TensorFlow constant so they can be used efficiently in the data pipeline. By making the paths a constant, they become part of TensorFlow's computational graph. This allows TensorFlow to manage the file paths more effectively during dataset creation and processing. This function simulates different processing speeds for lines in a file. It splits each line at the comma, treating the first part as a delay factor and the second part as the numeric value to keep. The delay factor is converted to a floating point number, multiplied by 2000, and turned into an integer to control how long the function performs a busy wait. After this simulated delay, the function returns the extracted floating point value from the second part of the line. We build a TensorFlow dataset from a list of file paths, so each path becomes one element, then use a flat map operation to turn each file into a sequence of text lines processed one file at a time. Each line is passed through a custom parsing function that includes simulated delays and is restricted to a single parallel call to keep the pipeline strictly sequential. After parsing, we group the data into batches of 16 elements to make processing more efficient. Finally, we prefetch one batch ahead, so data preparation overlaps with model execution, and return this sequential dataset ready for further processing or analysis. We build a TensorFlow dataset from a list of file paths, so each path becomes an element, then use an interleave operation to read from several text files in parallel. Each file is treated as a dataset of lines, with a limited number of files and lines processed at a time, and TensorFlow automatically tunes the level of parallelism. We then apply a mapping function to each line that simulates a delay, again using automatic parallel execution. To improve performance, the dataset is cached in memory, batched into groups of 16 elements, and set to prefetch one batch ahead, so data is ready as soon as it is needed. The function finally returns this optimized, ready-to-use dataset. This function measures how long it takes to process an entire dataset. It records the start time, then loops through each batch, counting how many batches there are and how many individual elements are processed in total. After all batches have been handled, it computes the elapsed time by comparing the current time to the start time. Finally, it prints a brief summary that includes the dataset label, the total number of batches and elements, and the total processing time rounded to 3 decimal places. We first build a sequential dataset that reads files one at a time and processes each line in order. Then we build an interleaved dataset that reads from multiple files at once to improve processing efficiency. With both datasets prepared, we can run further operations, such as measuring throughput, to compare how well sequential and interleaved data handling perform. We begin by taking a single batch from the sequential dataset and another from the interleaved dataset, using an iterator to retrieve the first batch from each. These batches are stored separately so we can inspect them. We then print the shape of the first batch from the sequential dataset to check its dimensions and confirm the data looks correct. Next, we print the shape of the first batch from the interleaved dataset for the same reason. These checks are important for debugging and ensuring both data pipelines are structured properly before moving on to performance comparisons. We first measure how long it takes to process all batches using a sequential dataset pipeline to determine its data throughput. Then we repeat this timing for an interleaved dataset pipeline, which reads from multiple files at the same time. By comparing the total processing times, we can judge how much more efficient interleaving is than sequential processing in terms of throughput. This script uses TensorFlow to compare the performance of sequential and interleaved data pipelines. It builds small temporary text files with delay factors, then processes them either one file at a time or by reading several files concurrently. Both pipelines simulate delays while parsing lines, then batch and prefetch the data for efficiency. The script prints the TensorFlow version, shows the shape of the first batch from each pipeline, and measures how long it takes to process all the data. In practice, the interleaved pipeline usually achieves higher throughput, finishing the work faster than the sequential pipeline because it reads multiple files at once and benefits from caching. Caching memory versus disk. When choosing between caching data in memory or on disk for a pipeline, focus on how it affects speed and resource use. In-memory caching keeps transformed data in RAM after the first pass, so later epochs can access it quickly, which is especially helpful when the dataset fits in memory and you loop over it many times, such as in multi-epoch training. This reduces time spent reading from storage and helps keep the GPU busy. However, RAM is limited and shared, so you must balance these performance gains against the risk of exhausting memory and causing instability or failures. Disk caching stores processed datasets on local solid-state drives or fast network storage, providing a scalable and robust alternative when data cannot fit in memory. Although it is slower than using RAM, it is still much faster and more predictable than repeatedly parsing data from slower storage each time you train. This is especially useful for very large datasets, such as recommendation systems with millions of records, where parsed features can be reused across training runs. By caching to disk, you create a reusable snapshot of your data that can support multiple experiments and training jobs, as long as the pre-processing steps stay the same. Choosing between memory and disk caching is a strategic decision that depends on profiling your system and understanding your workload. If your pipeline is limited by input and output speed and the dataset is small, caching in memory can make access almost instant. For larger datasets or limited memory, disk caching on fast solid-state drives is often more practical. Many teams combine both approaches, using disk caching during early exploration and switching to memory caching for optimized runs. Overall, treat caching as a flexible layer in your pipeline that you can adjust as needs change without redesigning everything. Python code, caching memory versus disk. This script demonstrates the difference between memory caching and disk caching when working with a small synthetic image dataset. Its main goal is to show how caching affects performance in a TensorFlow data pipeline. By focusing on basic cache behavior, it helps you understand when and why memory or disk caching might be more efficient for your data loading process. The line with the exclamation mark is a command to install TensorFlow version 2.20.0. It makes sure the script uses the exact TensorFlow version it was designed for, which helps prevent compatibility problems with other versions. You typically run this command in a terminal or notebook before running the rest of the script, so the required library is properly set up. We start by importing 3 key Python libraries. The operating system library lets us work with files, folders, and other system features. The time library allows us to measure how long operations take, which is useful for checking performance. The pathlib library provides an object-oriented way to handle file system paths, making path management more convenient and consistent across different operating systems. We start by importing TensorFlow, the main library we use to build and train machine learning models. After that, we print the TensorFlow version in use. Knowing the exact version is important because different versions can change available features and syntax. This helps ensure our code is compatible and behaves as expected. We begin by setting a fixed seed value so that any random operations in our code produce the same results every time it runs. This is important for reproducibility, especially when training or testing machine learning models. In this example, we choose the number 42 as the seed. We then apply this seed to TensorFlow's random number generator so that all TensorFlow operations that rely on randomness behave consistently across different runs. We begin by setting up the basic parameters for our synthetic image dataset. First, we choose to generate a total of 256 images. Then we define the shape of each image as 28 by 28 pixels, with one color channel, which corresponds to grayscale images. These settings establish both how many images we will create and the exact size and format of each one, ensuring consistency throughout the dataset. The function starts by creating synthetic images using a random uniform generator in TensorFlow. It builds a tensor whose shape is set by the desired number of images and their image dimensions, and fills it with pixel values that are random floats between 0 and 1, stored as 32-bit floating point numbers. A fixed random seed is used so that the same synthetic images can be generated again in future runs. This reproducible randomness is important for consistent testing and debugging. This operation uses TensorFlow to create a tensor filled with zeros with one entry for each image in the dataset and stores these values as 32-bit integers. The tensor serves as the label set for a synthetic dataset, meaning every image is initially assigned the label 0. This setup is useful when you want a simple dataset that emphasizes image processing tasks without introducing complex or varied labels. This part of the code builds a TensorFlow dataset from the synthetic images and their labels. It uses a method that takes both as input and pairs each image with its correct label. The result is a dataset where each element is one image and its corresponding label. This structure is essential for later steps, such as processing the data and training machine learning models. We begin by generating a base dataset of synthetic images using a function that takes the number of images and their shape as inputs. This function creates random images drawn from a uniform distribution and uses a fixed seed, so the results are reproducible. Each image is assigned a simple label of 0. Finally, we convert this collection of images and labels into a TensorFlow dataset object so it can be handled and preprocessed efficiently in later steps. The preprocess function prepares images for training by applying several optimized steps. It first flips each image horizontally as a form of data augmentation to increase variety in the dataset. Next, it randomly adjusts the image brightness within a small range using a fixed seed so the results are reproducible. Finally, it standardizes the pixel values to have 0 mean and unit variance, which helps stabilize the training process. The function then returns the processed image together with its original label. This function packages the image preprocessing steps so they can be used with TensorFlow's data mapping. It takes an image and its label, applies the predefined preprocessing operations to the image, such as flipping, brightness adjustment, and standardization, and leaves the label unchanged. It then returns the transformed image together with the original label. This makes it easy to apply the same preprocessing to every element in a dataset using TensorFlow's map operation. To build the data pipeline, we first shuffle the base dataset with a fixed random seed so the order is randomized but still reproducible. This helps prevent the model from learning patterns based only on data order. We then apply a preprocessing function to each data element using a mapping operation that flips images horizontally, randomly adjusts their brightness, and standardizes them. This mapping is run in parallel, with TensorFlow automatically choosing how many parallel calls to use for better performance. This part of the code chooses whether to cache the dataset in memory or on disk. When the memory option is enabled, the dataset is stored in memory, which makes later access faster because it avoids reading from disk. If that option is not used, the dataset is cached to a file on disk instead. Storing it on disk is helpful when memory is limited or when you want the dataset to remain available across different sessions. The dataset is split into batches of 32 images to control memory use and speed up processing by working on smaller chunks. It is then configured to prefetch these batches automatically, so data loading and preprocessing happen in parallel with model execution. This overlap keeps the model from waiting for new data, reduces idle time, and improves overall throughput. Finally, the prepared dataset is returned for further processing or training. This function measures how long it takes to process one full epoch of a dataset. It records the start time, then loops through each batch in the dataset while counting how many batches are processed. After all batches are handled, it records the end time. Finally, it prints a message with the given label, the total number of batches, and the total epoch time rounded to 3 decimal places. This provides a simple way to evaluate the performance of the dataset processing pipeline. We start by creating a directory using a path library to store cache files, giving it a specific name, and making sure it exists. The directory creation is set up so it does nothing if the folder is already there, which avoids errors. We then build the full path to the cache file by combining this directory with a chosen file name. This complete path will later be used to save cache data to disk. We build a data pipeline that keeps the dataset in memory to speed up training. By configuring the pipeline to cache in RAM, data can be retrieved much faster in later epochs. The pipeline also shuffles the data, applies a preprocessing function, then caches, batches, and prefetches it. Together, these steps optimize how data flows to the model during training. We are building a data pipeline that stores its cache on disk instead of in memory. To do this, we call the pipeline building function, give it a file location for the cache, and disable memory caching. As a result, the dataset is written to disk, which is helpful for large datasets that do not fit into RAM. This setup also lets us later compare how disk caching performs relative to memory caching in our operations. We begin by printing a message to indicate that we are timing the first epoch while using memory caching, so it is clear that the cache is being filled during this initial run. Then we call a timing function on the dataset that uses memory caching and label this run as the first memory epoch. This function measures how long it takes to process the entire dataset, including the cost of populating the cache. The recorded time helps us understand the performance impact of enabling memory caching during the first epoch. We begin by printing a message to indicate that we are timing the second epoch using the memory cache, which keeps the dataset in RAM for faster access. Next, we call a timing function that processes one full pass over this in-memory dataset. As it runs, the function iterates through all batches, counts how many there are, and measures how long the entire epoch takes. We label this timing run as memory epoch 2 so it can be clearly identified in the output. We start by timing the first and second epochs when using a disk cache. A message is printed to mark the beginning of the first epoch, where the cache file is written to disk, setting up the measurement of how long it takes to process the dataset with disk caching. Then we call a timing function for one full epoch, giving it the disk-based dataset and a label for the first disk cache epoch. This function iterates over the dataset, counts the number of batches, and records the total time, allowing us to evaluate the performance impact of caching data on disk. We first print a message to indicate that we are starting the second training epoch using the disk cache, which sets the context for what follows. Then we call a timing function that measures how long it takes to process the entire dataset when the data is read from the cache on disk. This function runs through the full dataset, records the total processing time, and prints the result with a label showing that it corresponds to the second epoch with disk caching. The code cleans up the cache file by first checking through the operating system's path tools whether the file exists. If it does, the file is deleted. This removes any temporary cache data stored on disk, frees space, and helps avoid conflicts the next time the program runs. This script uses TensorFlow with a synthetic image dataset to compare the performance of memory caching and disk caching. It creates random images, applies simple preprocessing, and then builds two data pipelines, one that stores cache data in memory and another that stores it on disk. In both cases, the first training epoch is slower because the cache is being filled, but later epochs run faster. The memory cache is quicker overall because accessing data from memory is faster than reading it from disk. After the run, the script removes the disk cache file, highlighting how different caching strategies affect data processing speed in machine learning workflows. Randomness, performance, trade-offs. When you combine interleaving, caching, and parallelism in an input pipeline, you must consider how they affect data randomness, not just shuffling. The key issue is how unpredictably the pipeline samples from different files or classes. Strong interleaving can mix data sources well, such as logs from different days, and produce diverse mini-batches. However, caching too early can freeze one particular random order, so later epochs see less variety. Over many epochs, this reduced randomness can introduce subtle bias and harm generalization, especially for large models. When optimizing a data pipeline, you must balance strong randomness with efficient use of resources. High randomness often requires heavy shuffling and parallel reads, which can greatly increase CPU and memory usage, especially in tasks like computer vision with many image files and complex augmentations. Techniques such as caching processed data or reducing the intensity of shuffling can improve throughput, but they may lower the diversity of data seen during training. The key challenge is to find a compromise that preserves enough randomness for reliable learning, while still allowing fast, efficient training. When managing randomness and performance in data pipelines, you need to balance caching, interleaving, and parallelism. Caching early can speed things up, but may fix the data order and reduce randomness between epochs, while caching later preserves randomness but uses more resources. Increasing interleaving and parallelism can improve both randomness and throughput, yet too much can actually slow the system down. A good approach is to start with strong randomness, then gradually adjust caching and parallelism to find the best trade-off between speed and model quality for your specific project. Python code, randomness, performance trade-offs. This script explores the trade-off between randomness and performance when working with data pipelines. It uses a very small synthetic dataset built with TensorFlow data tools to keep the focus on how different pipeline options behave. In particular, it examines how interleaving, shuffling, and caching affect both the randomness of the data order and the timing of data delivery. The goal is to understand how these settings influence efficiency and variability in a controlled, simple setup. The line that begins with an exclamation mark is a command to install TensorFlow version 2.20.0. Specifying this exact version makes sure the script uses the expected features and behavior of that release. This helps avoid problems that can occur if a newer or different version of the library changes how things work. We begin by importing 3 standard Python libraries: OS, time, and random. The OS library lets us interact with the operating system, which is useful for tasks like working with environment settings or file locations. The time library helps us measure how long operations take, which is important for analyzing performance. The random library generates random numbers, which we rely on to create controlled randomness in our dataset operations. We start by importing TensorFlow, which we need to build and manage the data pipelines used in this script. After that, we print the TensorFlow version so we know exactly which release is running. This helps us check compatibility and understand how the code might behave, since different versions can offer different features or performance. We set a seed value of 42 so that any random operations in our code produce the same sequence of numbers every time we run it. This makes our results reproducible and easier to compare across runs. We also set the Python hash seed to the same value so that any hashing behavior that might involve randomness is consistent as well. Together, these steps make the script behave deterministically, which is important for reliable debugging and testing. We create a small synthetic dataset by defining 6 distinct files, which represent 6 different file identifiers. Each file is assigned 20 examples, so it contains 20 individual data points. These simple settings give us a manageable dataset that is useful for testing and comparing different data processing strategies. We begin by generating a list of fake file identifiers using a range of numbers from 0 up to, but not including, the total number of files. This list serves as a simple synthetic dataset representing all our files. We then check the length of this list and print how many fake files it contains. This confirms the dataset size and helps ensure everything is correctly prepared for later processing. We define a function that simulates reading a file by taking a file identifier and creating a TensorFlow dataset of example indices for that file. The dataset generates numbers from 0 up to 1 less than the number of examples in the file, representing each example's position. We then use TensorFlow's mapping operation to convert each index into a pair that includes the file identifier and the example index. The function finally returns this dataset of file and index pairs, ready for further processing. The function starts by turning the list of file identifiers into a TensorFlow dataset so it can be processed efficiently. It then checks whether file shuffling is enabled. If shuffling is turned on, it randomizes the order of the files using a buffer size equal to the number of files. This shuffle step uses a fixed random seed so that the randomized order is reproducible across different runs. This code uses TensorFlow's data pipeline to interleave examples from multiple files. It applies an interleave operation to a dataset of file identifiers using a small function that reads each fake file based on its identifier. The cycle length and number of parallel calls are both set to the same interleave parallel value, so several files can be processed at the same time. The deterministic setting is enabled to keep the output order consistent across runs, which is important for reproducible results. This part of the code checks whether the cache before shuffle option is turned on, and if so, it caches the dataset. Caching stores the data in memory after the interleave step but before shuffling, which can speed things up by avoiding repeated reads from disk when the dataset is used multiple times. However, doing this can reduce randomness because the same order of examples will be reused each epoch unless you explicitly reshuffle later. The code randomly shuffles individual examples in the dataset to improve randomness during training. It uses a large buffer based on the total number of files and examples per file to ensure a good mix of data points. A fixed seed is set so that the shuffle order is reproducible and remains the same each time the code is run. In addition, reshuffling is performed at every new pass through the dataset, maintaining randomness across multiple iterations while still being repeatable. The dataset is divided into batches of 8 examples to make it easier to inspect and process in manageable chunks. A setting is used so that if the total number of examples is not a multiple of 8, the final smaller group is still kept instead of being discarded. The result is a batch dataset that includes all examples and is ready for further processing or analysis. The function starts by recording the current time so it can measure how long the process takes. It then creates an empty list to hold the first few batches of data. This setup allows the function to capture and store the initial batches within a set limit. By doing this, it becomes possible to track and compare the performance of different data pipelines based on how these early batches are processed. We iterate over the dataset with an index so we can track how many batches have been processed and stop once we reach a chosen maximum, avoiding extra computation. For each batch we do process, we take the first example and store it in a list called first batches. Later, we analyze the source files of these first examples to study how random the sampling is and how well the data pipeline performs. The code measures how long the operation takes by subtracting the recorded start time from the current time. It then multiplies this time difference by 1,000 to convert seconds into milliseconds. Using milliseconds gives a more precise measurement of the data pipeline's performance and helps evaluate how long the process actually took. The code first collects the file identifiers from the first element of each batch and converts them to integers using TensorFlow's NumPy method, making the file IDs easier to read. It then prints a brief summary that includes the label of the current pipeline configuration, the elapsed time in milliseconds rounded to 2 decimal places, and the list of these first file identifiers. This summary offers a quick view of how the pipeline is performing and how its randomness is behaving across batches. We set up a data pipeline called pipe_strong_random that is optimized for maximum randomness. It shuffles the order of files before processing and interleaves examples from multiple files using 4 parallel threads to improve throughput. We also choose not to cache the data before shuffling, so the data is read and shuffled on the fly. This design favors highly random data ordering, even though it may reduce performance compared to cached or less shuffled pipelines, and is best suited for situations where randomness is more important than speed. We configure a data pipeline by first creating the pipeline, then enabling shuffling of file order to add randomness to the data. We set interleave parallelism to 4 so that examples from up to 4 files can be processed at the same time. We also enable caching before shuffling, so the data is stored in memory, which can speed up later accesses and improve overall performance by reducing data loading time. We configure this data pipeline to run in a simple, sequential way. We disable file shuffling, so files are processed in their original order. We set the interleave parallel setting to 1, so only one file is handled at a time, limiting parallel processing. We also choose not to cache data before any shuffling. Overall, this setup minimizes randomness and parallelism in favor of a straightforward, ordered workflow. We run 2 training epochs to study how different pipeline settings affect randomness and performance. For each epoch, we announce the epoch number, then call the run epoch procedure 3 times with different configurations. One configuration emphasizes strong randomness, another caches data early, and a third reduces parallel processing. Each configuration processes up to 3 batches, so we can compare timing and the order in which files are handled. This experiment helps us see how changing the pipeline impacts both speed and the randomness of data processing. This script uses TensorFlow data pipelines to compare how different levels of randomness affect performance. It builds a synthetic dataset of file identifiers, simulates reading them, and then tests 3 pipeline setups: one with strong shuffling of both files and examples, one that caches data early before shuffling, and one that processes files with low parallelism. Each setup is run for 2 epochs, and the time to process several batches is measured. The results show that stronger randomness can slow processing, early caching can speed things up but reduce randomness, and low parallelism further limits randomness and may increase processing time. Overall, the experiment highlights the trade-off between randomness and speed in data pipeline design. Parallel input optimization. Automatic parallel calls. Automatic parallel calls are important for efficient input pipelines in distributed training because they let preprocessing run on many data elements at the same time. This is especially critical when feeding multiple GPUs or workers that consume data quickly, so the devices do not sit idle waiting for input. While the models run, CPU cores can simultaneously decode images, parse text, and perform other complex tasks, ensuring that batches are ready when needed. As a result, data preparation scales across cores without the user having to manage threads manually. In distributed training, automatic parallel calls help the input pipeline keep up when many replicas request data at the same time. They increase throughput by allowing more concurrent work, such as parsing and feature engineering, without manual tuning. At the same time, the system avoids overloading the host machine, which could cause problems like excessive context switching and cache thrashing. It does this by automatically choosing an appropriate level of parallelism based on available CPU resources and operation costs, adapting to both powerful workstations and smaller servers. Automatic parallel calls are most useful when you scale from a single device to many devices without changing your input pipeline. For example, when training a recommendation model on multiple GPUs, they let complex data operations run with higher concurrency, so the input pipeline keeps up with more replicas. In cloud environments where hardware details are often unknown, this feature adapts itself to the available infrastructure. As a result, it improves device utilization, shortens training time, and helps maintain consistent performance across different deployments. Python code, automatic parallel calls. This script demonstrates how automatic parallel calls work in a simple way. It builds a small data pipeline for images using TensorFlow tools, then compares the behavior of automatically managed parallel calls with manually configured parallel calls. The goal is to show how these two approaches differ when processing image data in parallel. This line is a comment that recommends installing TensorFlow version 2.20.0. It serves as a setup instruction to prepare the environment before running the rest of the code. Using this exact version helps ensure that the script behaves as expected and that all required TensorFlow features are available and compatible. We start by importing 3 key libraries. The operating system library lets us work with files and environment settings. The random library is used to generate random numbers, which is helpful for setting seeds and making results reproducible. The time library allows us to measure how long different parts of our code take to run. We begin by importing NumPy and TensorFlow to prepare the environment for numerical computing and machine learning. NumPy is used for fast and efficient array operations, while TensorFlow provides the tools to build and train neural networks. These imports are required so that the rest of the script can access the functions and features needed to run correctly. This code displays the version of TensorFlow that is currently installed and running. Knowing the exact version helps you check compatibility with your code and libraries. It also clarifies your environment setup, which is important because TensorFlow features and behavior can change between versions. The code first uses a TensorFlow function to list all physical devices and check specifically for any available GPUs. This step determines whether the system has graphics processors that can be used to speed up computations. It then prints how many GPUs were found, giving you a clear idea of the hardware resources available for parallel processing. The code first checks how many physical GPUs are available, and then chooses an appropriate distributed training strategy. If there is more than one GPU, it uses TensorFlow's mirrored strategy to train synchronously across all GPUs, keeping model variables mirrored and in sync on each device. If there is only one GPU or none at all, it falls back to TensorFlow's standard single-device strategy. This approach lets the model automatically make efficient use of whatever hardware is available during training. We begin by setting a seed value of 42 so that all random operations are reproducible. We apply this seed to Python's built-in random number generator, then to NumPy's generator, and finally to TensorFlow's generator. Using the same seed ensures that any random numbers or random behavior in these libraries are consistent each time the code is run. This deterministic setup is important for reliable debugging and for comparing results across different runs. We begin by loading the MNIST dataset using a helper function from Keras, which gives us separate sets of training images and their labels. MNIST is a standard collection of handwritten digit images commonly used to train and evaluate image processing and machine learning models. Loading the data in this way makes it straightforward to access, organize, and manipulate the images and labels for our learning tasks. To speed up code execution, a smaller subset of the MNIST training data is used instead of the full dataset. Specifically, only the first 4,096 images and their labels are selected. This reduces the amount of data that needs to be processed, which makes testing and development faster while still allowing the model to be trained and evaluated. Before building the dataset, The code first checks that the number of images matches the number of labels. This step ensures that every image has a corresponding label. Maintaining this one-to-one match is essential for data integrity and is crucial for supervised learning tasks, where the model learns from correctly paired inputs and outputs. The preprocess function takes an image and its label, converts the image to floating point values, and normalizes the pixel values to lie between 0 and 1. It then adds a channel dimension so the image matches the format expected by single-channel models, such as those for grayscale input. The image is resized to 32 by 32 pixels to give the model a consistent input size. Finally, the function randomly flips the image horizontally to add variation and improve the model's ability to generalize, and then returns the processed image with its original label. The preprocess function prepares each image for a convolutional model by first converting it to floating point values and normalizing the pixels to range between 0 and 1. It then adds a channel dimension so the data matches the expected three-dimensional input format. The image is resized to 32 by 32 pixels to keep the input size consistent. A random horizontal flip is applied to add variation and improve the model's ability to generalize. The function finally returns this processed image together with its original label for supervised learning. We begin by building a base dataset from the MNIST training images and their labels using TensorFlow's data tools. This creates a dataset object that holds the image and label pairs together. With this structure in place, we can efficiently manage the data and apply operations like batching and shuffling. These steps are essential to prepare the data properly for training machine learning models. The data set is first shuffled using a buffer the same size as the subset, so the data is thoroughly mixed, which helps reduce order bias during training. A fixed seed is used, so this shuffling is consistent across different runs. After shuffling, the data is split into batches of 64 examples. Processing data in batches lets the model handle multiple samples at once, improving computational efficiency and helping to stabilize gradient updates during training. This code uses TensorFlow's caching feature to store the dataset in memory after it has been processed once. On later accesses, the data can be reused directly without being decoded or processed again. This makes data loading faster and reduces computational work. It is especially helpful when the same dataset is used many times because it improves overall performance. We create the dataset by applying the preprocessing function to each element using TensorFlow's map operation, which can run in parallel. Automatic tuning is used to choose how many parallel calls to make based on the available hardware. We then use prefetching so that the next batch of data is prepared while the current batch is being processed. Automatic tuning also selects how many batches to prefetch, which helps make data loading and processing more efficient. We begin by creating a new dataset from the base dataset using a mapping operation that applies the preprocessing function to each element with only one parallel call, so it handles one element at a time. We then add a prefetch step with a buffer size of 1, which lets the system prepare the next element while the current one is still being processed. This simple setup helps us observe how performance changes when moving from manual, single-element processing to more automatic parallel processing. Within the strategy scope, we build a simple neural network using a sequential Keras model. It takes 32 by 32 grayscale images as input, then applies a two-dimensional convolutional layer with several filters and ReLU activation to learn spatial features. The result is flattened and passed to a final dense layer with 10 units and softmax activation to produce class probabilities for 10 categories. We compile the model with the Atom optimizer, use sparse categorical cross-entropy as the loss function, and track accuracy as the main performance metric. This function measures how long it takes to train a model for one epoch on a given dataset. It records the start time, runs the training for a specified number of steps without detailed logging, then records the end time. By subtracting the start time from the end time, it computes the total training duration. It also extracts the final accuracy from the training history. Finally, it prints a brief summary of the run, reporting the rounded training time and accuracy. This function measures how long it takes to train a model on a specific dataset for one epoch and reports the resulting accuracy. It records the start time, trains the model for one epoch with a fixed number of steps while hiding detailed output, then records the end time. The training duration is found by subtracting the start time from the end time, and the final accuracy is taken from the training history. It then prints the dataset description along with the rounded training time in seconds and the rounded accuracy to summarize performance. To make timing measurements more consistent, we first run a short warm-up phase for the model. In this phase, the model is trained on a small subset of the data, using only 5 batches from the automatic dataset. We run this for one pass through these batches, so the model processes each batch once. The training output is turned off during this step. This warm-up allows the model to initialize its internal states so that later timing results are more stable and reliable. We measure the training performance of the dataset that uses manual parallel calls by timing one training epoch. A timing function records the start time, runs the model's training method for a single epoch on this dataset, then records the end time. It computes how long the epoch took. It also reads the accuracy from the training history. Finally, it prints a short description along with the training time and accuracy, both rounded to 3 decimal places, so we can see how manual parallel calls affect speed and accuracy. We now measure how long it takes to train the model for one epoch using a dataset that automatically chooses the number of parallel data processing calls. The training function records this time, so we can evaluate the performance of this automatic setting. We label the result as automatic parallel calls to clearly distinguish it and compare its efficiency with the manual parallel calls approach. To check that the data pipeline works correctly, we take a single batch from the dataset that was created with automatic parallel processing. We then iterate through this batch of images and labels and print the shapes of both. By inspecting these shapes, we can confirm that preprocessing and batching were applied as intended. This ensures that the images are properly resized and that each image is correctly paired with its label. This script uses TensorFlow's data pipeline tools to compare automatic and manual parallel processing during model training. It sets up a reproducible environment, loads part of the MNIST dataset, and applies a pre-processing step that normalizes and augments the images. 2 datasets are built, one that relies on automatic parallel calls and one that uses a single manual parallel call. A simple convolutional neural network is trained under a distributed strategy that adapts to the number of available GPUs. The script measures and compares training times for both datasets, typically showing that automatic parallelization is faster because it uses resources more efficiently. It finishes by printing the shape of a batch from the automatically parallelized dataset to confirm that the data pipeline is working as intended. Parallel mapping strategies. Parallel mapping is essential for building efficient input pipelines in distributed training because it controls how many examples are processed at once and how work is spread across CPU cores and devices. When tasks like image decoding or data augmentation are done one example at a time, the system can become a bottleneck, leaving GPUs or TPUs waiting for data. The aim is to overlap preprocessing across many elements so the data production rate matches the consumption rate of all replicas. By properly tuning parallelism in the mapping stage, you can avoid idle accelerators and turn a slow preprocessing step into a concurrent system that fully supports distributed training. When designing a parallel mapping strategy, first consider how costly and variable your preprocessing tasks are. Simple operations like scaling may need little parallelism, while heavier work such as image augmentation or text tokenization can benefit from using many CPU cores. In distributed setups, the mapping stage should produce data fast enough to feed all replicas without overloading the system. As you move from a single device to multiple devices, adjust the level of parallelism to match changes in batch size, model complexity, and dataset characteristics so that additional GPUs are not left underutilized. Parallel mapping must be balanced with other pipeline stages and system resources, especially CPU and memory, to avoid contention that slows processing and lowers throughput. The practical approach is to profile the pipeline under realistic workloads and gradually increase parallelism until performance gains level off. This helps ensure accelerators are well utilized without overloading the host system. Because optimal settings depend on the current cluster size and hardware, teams regularly adjust their parallel mapping strategy as the system evolves. Python code parallel mapping strategies. This script demonstrates how different parallel mapping strategies work by directly comparing their performance to a standard sequential map. It focuses on measuring how much faster or slower parallel mapping can be in practice. To keep the comparison simple and controlled, it runs these methods on a small, synthetic image dataset. The line with the exclamation mark and the pip install command tells the system to install TensorFlow version 2.20.0. This makes sure the script uses the correct TensorFlow version and helps prevent compatibility problems with other versions. The exclamation mark also indicates that this command is intended to be run in a Jupyter notebook or a similar environment where you can execute shell commands directly from the notebook. We start by importing 3 key libraries. The operating system library lets us interact with the system for tasks like working with files and managing the environment. The time library allows us to measure how long operations take, which is important for performance benchmarking. The random library generates random numbers, which we can use for tasks such as setting seeds to make experiments reproducible. We begin by importing TensorFlow, a major library used for machine learning and deep learning. This gives us access to its tools for building and training models. We then check which version of TensorFlow is installed, because different versions can have different features and compatibility. Knowing the version helps ensure that our code will run correctly and behave as expected. We begin by setting a global seed value, such as 42, so that any random operations in our code are repeatable. Using this seed to initialize the random module makes the sequence of random numbers the same every time we run the program. This consistency is important because it ensures our results are reproducible across different runs. We begin by importing the numerical computing library NumPy, then set its random seed using a chosen seed value. Setting the seed makes NumPy's random number generation repeatable. This means that every time we run the code with the same seed, we get the same random values. As a result, our experiments become consistent and reproducible. We set the random seed for TensorFlow using a predefined value so that any random operations it performs are reproducible. This means that running the same code multiple times will produce the same results. Such consistency is important for debugging and for reliably comparing different runs of an experiment. We start by printing the version of TensorFlow that is currently in use. Knowing the exact version helps us check compatibility with our code and libraries. It also tells us which features and performance characteristics we can expect, since these can change between versions. This code uses TensorFlow to check whether any GPU devices are available on the system. It calls a configuration function that lists the physical devices and looks specifically for GPUs. By doing this, it determines if GPU resources can be used to speed up computations. This is especially important for performance in tasks such as deep learning. This code checks how many physical GPU devices TensorFlow can detect, and then prints that number. By reporting the count of available GPUs, it gives a quick overview of the hardware resources you have. This helps you understand your system's capacity for parallel computation and how much acceleration you can expect for your TensorFlow workloads. We begin by setting up a synthetic image dataset with a total of 2,048 images, which provides a manageable size for testing. Each image is defined to have a height of 28 pixels. Together with the width and number of channels specified later, this shapes the images to follow a standard format similar to the MNIST dataset, which is widely used for training and evaluating image processing models. Each image in the dataset is defined as 28 pixels wide and 28 pixels high, so all images are square. We also specify that each image has a single channel, meaning the images are grayscale rather than color. These settings determine the shape of the image data and ensure that all images in the dataset follow a consistent format. We generate a small random image array in a repeatable way using a NumPy function that produces integer pixel values between 0 and 255, which is the usual range for image intensities. The array's shape is determined by constants that specify how many images we create, along with their height, width, and number of color channels. We store the data as unsigned 8-bit integers, a standard and efficient format for representing image pixels. We create simple labels for our dataset by using a random integer generator from a numerical library to produce values between 0 and 9. This gives us an array of random labels whose length matches the number of images. So each image has one label. We store these labels as 32-bit integers, which is a standard and efficient format for label data in many machine learning tasks. We convert the NumPy arrays of images and labels into a TensorFlow dataset so we can use TensorFlow's efficient tools for handling large amounts of data. This dataset format makes it easier to prepare data for machine learning workflows. Once in a dataset, we can conveniently apply operations such as shuffling, batching, and mapping. These steps are essential for organizing and transforming the data before training models. The dataset is shuffled using all available images as the buffer size so that their order is thoroughly randomized, which helps prevent the model from picking up unintended patterns. This setup mimics the natural randomness expected in training data and supports better generalization. A fixed seed value is used so that the shuffle process is deterministic, meaning the same random order can be reproduced consistently across different runs. We use a global batch size of 128, meaning that this many samples are processed together in each training or data processing step. Keeping the batch size consistent helps control memory usage and keeps it predictable. It also ensures that operations are applied in a uniform way across the entire dataset. The code groups the dataset into batches using a global batch size so the model can process several samples at once during training. This batching greatly improves efficiency and keeps the input size consistent. The option to drop any remaining samples that do not fill a complete batch ensures that every batch has the same size. This consistency is important for models that require fixed size inputs. The heavy preprocess function takes an image and its label, then prepares the image for later processing. It first converts the image data to a floating point format, so it can be used in operations that require this type. After that, it normalizes the image by dividing each pixel value by 255. This scales all pixel values to between 0 and 1, which is a standard step to help machine learning models work more effectively with image data. This code uses TensorFlow to randomly flip images horizontally as a form of data augmentation, turning them left to right. A fixed random seed is used so that the same images receive the same flips each time the code is run. This ensures the random transformations are reproducible and consistent across different runs of the training process. This code randomly adjusts the brightness of an image using a TensorFlow image processing function. The brightness is changed by a random amount within a limited range, with a maximum shift of 0.1. This controlled randomness adds variation to the training images and helps the model generalize better to new data. To simulate extra CPU work, the code builds a simple convolution kernel used for image smoothing. It is a 3x3 matrix where every entry is the same value, 1/9, created by filling the matrix with ones and dividing by 9. Applying this kernel to an image produces a smoothing effect and serves as a stand-in for a computationally intensive operation. The code performs a two-dimensional convolution on the image using TensorFlow, with a small kernel made of ones divided by 9. This kernel slides across the image 1 pixel at a time, because the stride is set to 1. The padding mode is set to keep the output image the same size as the input by adding zeros around the edges when needed. Overall, this convolution step is used as part of preprocessing to add extra computational work on the image. This function outputs the processed image together with its original label. By this final stage of the preprocessing pipeline, the image has gone through several transformations, such as normalization, random flipping, brightness changes, and convolution. The label is kept the same throughout, so the structure of the dataset is preserved. This allows the processed images and their correct labels to be used reliably for training or evaluating a model. We begin by creating a dataset using a sequential mapping setup, where a heavy preprocessing function is applied to each element of the base dataset, one at a time. This is done with a mapping method configured to use only a single parallel call, so the processing is strictly sequential. Using this approach allows us to later compare its performance directly with a version that uses parallel processing. The code uses prefetching on the sequential dataset to speed up training by overlapping data preparation with model computation. While the model processes the current batch, the system prepares the next one, which reduces idle time and increases throughput. TensorFlow's auto-tune feature automatically chooses how many batches to prefetch based on available resources, helping the data pipeline run efficiently without manual tuning. We configure the dataset to use parallel mapping so that processing is more efficient. Each element of the base dataset is passed through a heavy preprocessing function. By setting the number of parallel calls to TensorFlow's automatic tuning, the system chooses how many threads to use based on available resources. This automatic parallelization helps maximize throughput by better using the hardware for data processing. We use prefetching on the parallel dataset to speed up training by overlapping data loading with model execution. By setting the prefetch option to TensorFlow's automatic tuning, the system can choose how many elements to prefetch based on actual hardware performance. This reduces the time the model spends waiting for input data and improves overall throughput. We define a function to measure how long it takes to process one full pass, or epoch, over a dataset. To do this, we first record the current time using the time module. This starting time is then used as a reference point to calculate the total elapsed time for the epoch. The program starts by setting a step counter variable to 0, so it can track how many times a loop runs. Beginning at 0 means the counting is accurate from the very first iteration. As the loop executes, this counter will increase, allowing us to measure the total number of steps completed. The loop processes the dataset in batches of images and labels, and for each batch, it checks whether the number of images matches the expected global batch size. If the batch size does not match, the loop stops, so that only full, complete batches are used. This simple validation step helps maintain consistency in the data and prevents errors during later processing. This line of code computes the average value of the images in each batch using TensorFlow's reduce mean operation. It is intentionally lightweight and mainly acts as a stand-in for more complex calculations that would happen during real training. By doing this, we can simulate some processing work without changing the data itself. This allows us to focus on measuring how long data loading and preprocessing take. This line increases the step counter by 1 each time the loop finishes processing a batch of data. Each increment marks the completion of a single batch processing step. Tracking this count is important because it is later used to compute performance metrics, such as how many batches are processed per unit of time. This part of the code checks whether the current step count has reached or passed the target number of steps, and if so, it stops the loop. By breaking out of the loop at that point, the program limits how many times the loop runs. This control is important for setting the duration of the timing test and for making sure the loop does not continue running indefinitely. The code measures how long an operation takes by recording a start time, then later subtracting that start time from the current time. This subtraction gives the total elapsed time in seconds. In other words, it tells you the duration that has passed between when the process began and when it finished. This function returns two key results: the total time the process took and how many steps it actually completed. Together, these values show both the duration and the amount of work done. This information is useful for analyzing performance and understanding how efficiently the process ran. To choose a safe number of steps for timing, the code first finds how many full batches of data it can process. It does this by dividing the total number of images by the global batch size. The result is the number of complete batches available. Using only these full batches ensures that each time step processes the same amount of data, making the timing measurements consistent and reliable. The code limits how many steps it runs by choosing the smaller value between the total number of steps and 10. This cap keeps the runtime short and predictable. As a result, the measurement process stays quick and efficient, and tests do not take unnecessarily long to complete. Before timing the datasets, we first run through the sequential dataset once to warm it up, which initializes any needed resources or caches. We then do the same warm-up pass over the parallel dataset. This preparation step ensures both datasets are in a similar, ready state, so that the performance measurements we collect are fair and consistent. We begin by measuring the throughput of the dataset that uses sequential mapping. To do this, we call a timing function that records how long it takes to process one epoch, given the sequential dataset and a specified number of steps. The function returns the total time taken and the number of steps completed. We store these results so we can later compare them with the performance of the parallel mapping approach. We now measure how fast the dataset can be processed when using parallel mapping. To do this, we call a timing function for a single epoch, giving it the parallel version of the dataset and the number of steps to evaluate. The function returns how long the epoch took and how many steps were completed, and we store these results for later. By comparing these values with those from the sequential version, we can see how much more efficient the parallel mapping approach is. To find the throughput of the sequential mapping process, we measure how many images are processed per second. We first multiply the number of completed steps by the global batch size to get the total number of images processed. Then we divide this total by the time taken for those steps, using a very small time value if the measured time is extremely close to 0. The result is the image processing rate, expressed in images per second for the sequential mapping strategy. To find how many images per second are processed with parallel mapping, first multiply the number of parallel steps by the global batch size to get the total images handled. Then divide this total by the time taken for the parallel mapping. If the time is extremely small, use a tiny positive value instead to avoid dividing by 0. This result is the throughput in images per second, which you can use to compare parallel mapping performance with sequential mapping. The code reports a compact comparison between sequential and parallel mapping. It shows how many steps the sequential mapping takes and how long it runs. The time is rounded to 3 decimal places to keep the output easy to read. Overall, this gives a quick sense of the performance of the sequential mapping approach. The code reports how long the parallel mapping process takes. It prints the number of steps performed and the total execution time, rounded to 3 decimal places. This timing information lets you compare how efficient the parallel version is relative to a sequential approach. The code reports how many images are processed per second when using a sequential mapping strategy. It converts this performance value to an integer, so the output is cleaner and easier to read. This single number serves as a straightforward metric for judging the speed of the sequential data processing pipeline. This line reports how many images are processed per second when using parallel mapping. It converts the measured throughput into a whole number so the output is easier to read. The main purpose is to clearly show the performance gain achieved by processing images in parallel. The code computes how much faster parallel processing is compared to sequential processing by dividing the number of images handled per second in parallel by the number handled per second sequentially. This ratio represents the parallel speedup factor. The result is rounded to 2 decimal places for clarity, and then printed, giving a quick sense of the performance improvement gained from using parallel processing. This script compares sequential and parallel data processing in TensorFlow using a synthetic dataset of small images and labels. It applies a computationally heavy preprocessing step and then measures how long it takes to process a fixed number of batches in each mode. By timing the runs and computing how many images are processed per second, the script shows that parallel processing is much faster than sequential processing. The printed results highlight the time taken, throughput, and overall speedup, illustrating the efficiency gains of parallel data handling in machine learning workflows. Accelerating GPU and TPU. When training with GPUs or TPUs, the main goal is to keep the devices busy by delivering data batches just in time. Your data pipeline should stay slightly ahead, reading and augmenting data while the accelerator finishes its current step. If the pipeline falls behind, the device sits idle, lowering utilization and increasing step time. A well-tuned pipeline overlaps host-side work with device operations, so the accelerator is never waiting for data, which becomes especially important in distributed training where any inefficiency is multiplied across many devices. To fully utilize GPUs and TPUs, the input pipeline must be fast and parallel enough to keep all replicas busy. In multi-GPU setups, each replica reads from its own shard of the dataset, and the pipeline should read and transform data concurrently. This is achieved by processing multiple examples in parallel on the CPU. Interleaving reads from different data sources and prefetching data so these steps overlap with training. On TPUs, large and fast batch processing puts even more pressure on the input pipeline, so you often need extra parallelism careful placement of tasks like image decoding on the host, and sometimes a staged pipeline that prepares data well before the TPU core is needed. Modern accelerators like GPUs and TPUs only reach their potential when data is delivered to them quickly and in parallel. If tasks like decoding images or tokenizing text run too slowly on a single CPU thread, the accelerator sits idle, and adding more devices does not help. To avoid this bottleneck, the input pipeline must be optimized with parallel processing and prefetching so data is always ready when needed. By profiling and tuning these pipelines, you can keep each device well fed with data and achieve close to linear speedups as you add more accelerators. Python code, accelerating GPU and TPU. This script demonstrates how to optimize parallel input with a focus on using accelerators and distributed strategies. It introduces these ideas through small, simple examples that are suitable for beginners. The goal is to make it easier to understand how parallel input works in practical, accessible scenarios. There is a commented line included to install TensorFlow version 2.20, which is helpful if TensorFlow is not already available in your environment. If you remove the comment marker, this line will run and install that specific version for you. The installation is set up to run quietly, meaning it reduces extra messages and output during the process. We begin by importing a few key tools needed to work with TensorFlow. The operating system module lets us interact with the system environment, and the random module helps with generating random numbers for tasks like setting seeds and making results reproducible. We also import NumPy for efficient numerical work with arrays and mathematical operations. Finally, we bring in TensorFlow itself, which is the main library we will use to build and train machine learning models in this script. We set a seed value, such as 42, to make all random operations in our code reproducible. This means that each time we run the program, the random numbers generated will be the same. We apply this seed to the random module, to NumPy's random number generator, and to TensorFlow's random number generator. Doing so ensures consistent behavior in tasks like initializing neural network weights, which is essential for debugging and verifying results. This line checks and prints the version of TensorFlow currently in use. It helps you quickly confirm that the library is installed correctly and that your script is using the intended version. This matters because different TensorFlow versions can offer different features and may have different compatibility requirements. The code uses TensorFlow to check which hardware accelerators are available by listing physical devices of type GPU and TPU. This reveals whether the system has GPUs for faster computation and whether any TPUs are present. It then prints how many GPUs and TPUs were detected, giving a quick summary of the available accelerator hardware. To choose a distribution strategy, we first check the available hardware. If TPUs are present, we connect to them with TensorFlow's TPU cluster resolver and use a TPU strategy to take advantage of their parallel processing. If there are no TPUs, but GPUs are available, we switch to a mirrored strategy that replicates the model across all GPUs for parallel training. If neither TPUs nor GPUs are found, we fall back to a single device strategy on the CPU. This adaptive approach lets the code automatically match the best strategy to the hardware and optimize performance. The code checks how many replicas are synchronized under the chosen distribution strategy by reading the strategy's number of replicas in sync attribute. It then prints this value to show how many copies of the model are being trained in parallel. Knowing this number is important for optimizing training across multiple devices and making efficient use of available computational resources. We begin by loading the MNIST dataset, which consists of images of handwritten digits commonly used to train image processing models. For this demonstration, we only use a subset of 6,000 images and their labels taken from the start of the training data. This smaller selection keeps the dataset manageable while still being large enough to train our model. It also allows us to clearly demonstrate the overall training pipeline and how the accelerator is used. The training images are first converted to floating point values and normalized by dividing each pixel by 255 so that all pixel values fall between 0 and 1, which helps the neural network train more effectively. An extra dimension is then added to the data to represent the single image channel, giving it the four-dimensional shape expected by convolutional layers. Finally, the shape of this processed training subset is printed to verify the number of samples, the image height and width, and the single channel dimension. We use a preprocessing function that takes an image and its label, then prepares them for the model. It first resizes the image to 28 by 28 pixels, so all inputs have a consistent shape. It then applies a random horizontal flip to augment the data and increase variability, which helps the model become more robust. The function finally outputs the transformed image together with its original label for use in the data pipeline. We begin by turning the training images and labels stored in NumPy arrays into a TensorFlow dataset so we can use TensorFlow's efficient data pipeline tools. We then shuffle this dataset with a buffer size that matches the subset size, which helps ensure the samples are well mixed. The shuffling uses a fixed random seed so that the data order is reproducible each time we run the process. We begin by choosing a global batch size of 128, which is the number of samples processed together in each training step. We then divide this global batch size by the number of synchronized replicas to get the batch size for each replica, so the data is split evenly. If this division does not come out evenly, we still make sure that each replica processes at least one sample. This guarantees that every replica has data to work on, even when the global batch size is not perfectly divisible by the number of replicas. We optimize the data pipeline using TensorFlow's data tools by letting the system automatically choose how many parallel threads to use for data processing. A preprocessing function is then applied to each dataset element in parallel, which speeds up transformations by using multiple CPU cores. Finally, we cache the processed dataset in memory, so the transformations do not need to be recomputed every epoch, reducing data loading time and improving overall performance. This code uses an interleave style method to simulate reading from multiple file shards by turning each element into its own small dataset. It cycles through 4 elements at a time, which mimics parallel reading from 4 different sources. The number of parallel calls is set to be chosen automatically, so TensorFlow can adjust the level of parallelism based on available resources. Overall, this setup helps improve the input pipeline by overlapping data loading with model execution. We begin by batching the dataset using a fixed global batch size so that each batch has the same number of samples, which is important for efficient use of accelerators. Any leftover samples that do not complete a full batch are dropped to keep batch sizes uniform. We then enable prefetching so that data preparation on the host overlaps with model execution on the device. By letting the prefetch buffer size tune itself automatically, we reduce idle time and improve overall throughput by keeping data ready when the model needs it. We now distribute the optimized dataset using the chosen strategy so it can be processed in parallel across multiple devices. This approach ensures that each replica of the model receives its own portion of the data. As a result, training can efficiently use hardware accelerators such as GPUs or TPUs. This setup is essential for fully leveraging distributed computing when working with large datasets or complex models. We define a function that builds a small convolutional neural network using TensorFlow's sequential model. It starts with a two-dimensional convolutional layer with 16 3x3 filters and ReLU activation, taking 28 by 28 by 1 grayscale images as input. A 2x2 max pooling layer then reduces the spatial size, and the result is flattened into a one-dimensional vector. This is followed by a dense layer with 32 units and ReLU activation, and a final dense layer with 10 units and softmax activation to produce class probabilities for 10 categories, such as in the MNIST dataset. The function returns this complete model. Inside the distribution strategy scope, we create a new model so it is properly configured to run on accelerators like GPUs or TPUs. We then compile the model using the Atom optimizer with a learning rate of 0.001, which works well for large datasets and complex models. The loss function is set to sparse categorical cross-entropy, which is appropriate for multi-class classification tasks such as MNIST. Finally, we track accuracy as a metric to monitor how well the model performs during training. The model is trained using a fit operation that takes the distributed dataset as input and runs for a single epoch. So the model sees the entire dataset once. The number of steps per epoch is capped at 20, which limits how many batches are processed during that pass. Training output is turned off by setting the verbosity level to 0. This simple configuration is used to quickly illustrate how the data pipeline and hardware accelerators work together during training. We examine the model's final performance by taking the last recorded loss and accuracy values from the training history. These final entries show how well the model was doing at the end of the brief training run. We then print the loss and accuracy, each rounded to 4 decimal places to give a clear and concise summary of the model's results. This script shows how to build an efficient data input pipeline for training machine learning models in TensorFlow while taking advantage of GPUs and TPUs. It sets a fixed random seed for reproducibility, detects the available hardware, and chooses an appropriate distribution strategy for TPUs, GPUs, or the CPU. A subset of the MNIST dataset is loaded, normalized, lightly preprocessed, and then fed through an optimized TensorFlow data pipeline that uses parallel mapping, interleaving, batching, and prefetching to keep the accelerators busy. Within the chosen strategy, a small convolutional neural network is defined, compiled, and trained for a single epoch, and the final loss and accuracy are reported. Overall, the example highlights how to coordinate data loading and model computation across different accelerators to improve training efficiency. Debugging data pipelines. Quick dataset inspection. If you suspect your input pipeline is slowing down model training, first inspect the dataset itself. Simply iterate over a few elements to see what they return and how long they take, rather than using complex tools immediately. This quick check confirms that the dataset behaves as expected and can reveal initial delays such as directory scanning or cache building. For example, if the first batch is slow but later ones are faster, it points to startup overhead. By observing these patterns early, you can locate performance issues before moving on to more advanced debugging. When reviewing a data pipeline, inspect the structure and content of each element to spot hidden performance problems. If elements carry more data than needed, such as large media files or complex Python objects, you add unnecessary work and serialization overhead. Check that batch sizes are appropriate, tensors use the right format, and transformations are not duplicated. In some cases, like recommendation systems, pre-computing metadata instead of repeatedly joining it during processing can significantly reduce overhead. To diagnose performance issues in your dataset pipeline, measure how long it takes to load a few batches and compare that time to a training step. If data loading consumes a large share of the total time, it is likely a bottleneck. You may notice that only the first batches are slow due to caching or warm-up, or that all batches are consistently slow because of expensive operations on the CPU. These timing patterns reveal where time is being spent and help you decide whether to adjust parallelism, pre-compute transformations, or make other targeted optimizations. Python code. Quick dataset inspection. This script provides a quick way to inspect a TensorFlow data pipeline. It measures how long the pipeline takes to produce elements and shows the structure of those elements. By using it, you can quickly identify simple performance issues in your data input pipeline. The commented line is instructing you to install TensorFlow version 2.20.0. This ensures the code uses that exact version, which is important for compatibility. By fixing the version, the script can rely on specific features and behavior. This helps prevent errors that might occur if a different TensorFlow version were used. We start by importing 3 key libraries. The operating system library lets the script interact with the system, for example, to manage environment settings or file locations. The time library is used to measure how long parts of the script take to run, which is important for performance testing. The random library generates random numbers, and here it is used with a fixed seed so that the results are reproducible each time the script runs. We first set a fixed random seed so that any random numbers generated are the same each time the script runs, which makes results reproducible and easier to debug or compare. We also set the Python hash seed environment variable to a constant value. This controls how Python randomizes the hashing of objects, which can change the order of items in sets and dictionaries. By fixing both the random seed and the hash seed, we ensure consistent and repeatable behavior across different runs of the script. We start by importing TensorFlow, the main library we use to build and manage machine learning models. After that, we print the TensorFlow version currently running. Checking the version helps confirm compatibility and ensures we are working with the expected setup for our project. We begin by creating a small synthetic image dataset to test our data pipeline. We choose 64 samples, which sets how many images we will generate. We also set the image height to 28, which determines the dimensions of each image. This simple setup lets us simulate real-world image data in a controlled way, so we can inspect and validate our processing steps effectively. We use an assertion to make sure that both the number of samples and the image height are positive values. This check confirms that each of these parameters is greater than 0 before the program continues. If either value is 0 or negative, the assertion causes the program to raise an error. This safeguard is important because non-positive values for these settings would not make sense when building an image dataset and could cause problems later in the code. We create a simple test dataset by using TensorFlow to generate random grayscale image data, where each image is represented as a tensor with a specified number of samples, height, and a single color channel. We then generate random integer labels from 0 to 9, giving us 10 possible classes. These labels are stored in a tensor whose length matches the number of image samples. Together, this forms a basic set of images and corresponding class labels that can be used for testing and experimentation. The code uses TensorFlow's Data API to turn the image and label tensors into a dataset, which makes data handling and preprocessing more efficient. By wrapping the tensors in a dataset, you can later apply transformations and batching in a simple, consistent way. This step is essential for building a proper data pipeline that can feed data into a machine learning model in a structured and efficient manner. This preprocessing function takes an image and its label and prepares them for use in a TensorFlow data pipeline. It first converts the image to floating point values and normalizes the pixel values by dividing by 255, so they fall between 0 and 1. It then converts the label to an integer type, so it is ready for model training. Finally, it returns the processed image and label together as a pair. We begin by choosing a batch size of 8, which sets how many samples are processed together at once. We then take the base dataset and apply a preprocessing function to each element using a mapping operation. This function normalizes the image data and converts the labels into the correct format. After preprocessing, we group the data into batches of the chosen size, which makes training or evaluating the model more efficient. The code is configured to inspect 3 batches from the dataset, meaning it will only process and examine this small subset. This allows you to quickly check how the data pipeline is structured and how long each step takes. By limiting the inspection to a few batches, you can efficiently verify that everything works as expected without running through the entire dataset. We begin by recording the current time so we can measure how long it takes to process the data batches. This uses a time function that returns the number of seconds since a fixed starting point in the past. We also set up a variable to hold the time taken for the first batch, initially leaving it empty. With this setup, we can later calculate how long the first batch took and compare it with the total processing time. We iterate over a few batches from the dataset, unpacking the images and labels for each one. At the start, we record the current time so we can measure how long it takes to process the first batch. When we reach that first batch, we compute the elapsed time to get a sense of processing speed. For every batch, we then print the batch index and the shape and data type of both the images and the labels. This lets us quickly verify that the data has the expected structure and types before moving on. The code measures how long it takes to process all the inspected batches by subtracting the start time from the current time at the end. This calculation gives the total processing duration. That total time is then used to evaluate the performance of the batch processing. We report timing information for the dataset inspection to understand performance. First, we print how many seconds it takes to process the initial batch, which shows the startup overhead. Then we print the total time needed to process all inspected batches, giving an overall performance measure. Finally, we compute the average time per batch by dividing the total time by the number of batches, which is useful for comparing different configurations or datasets. This script quickly inspects a TensorFlow data pipeline by checking both timing and data structure. It begins by setting deterministic seeds and confirming the TensorFlow version, then creates a small synthetic dataset of grayscale images with random labels and wraps it in a TensorFlow dataset. A preprocessing step normalizes the images and converts labels to integers, and the data is batched into groups of 8. The script measures how long it takes to retrieve the first 3 batches and prints the shape and data type of the images and labels in each batch. Finally, it reports the time for the first batch, the total time, and the average time per batch to help spot simple performance issues in the pipeline. Profiling input performance. Treat your input pipeline as a measurable system so you can understand its performance instead of just guessing whether it feels fast or slow. Focus on how quickly it delivers data to the model, and look for times when the model is idle and waiting. Distinguish between the pipeline's steady throughput and its startup behavior, because a pipeline may start slowly but then run efficiently, or start quickly and then become a bottleneck during training. By profiling these patterns, you can make informed optimization decisions rather than relying only on overall training time. To profile input performance, separate the data pipeline from the training loop and measure how long it takes to process a fixed number of batches. This reveals the pipeline's throughput, how much batch times vary, and whether performance degrades over time. For example, in a medical imaging task, timing data retrieval and preprocessing can show if bottlenecks come from disk access, decompression, or other CPU work. If only the first few batches are slow, it suggests startup overhead, while consistently slow batches point to a deeper throughput problem that will affect the entire training process. Once you have timing data, examine how the input pipeline and model use resources together. Look for cases where the CPU is overloaded while the GPU is idle, or where input threads are blocked on reading data, and check whether prefetching keeps data preparation aligned with model execution. For example, in a recommendation system, parsing features may dominate CPU time and delay training steps. Effective profiling links step times with input delays, monitors prefetch buffer levels, and tests whether changes in parallelism or caching actually reduce step time. By measuring performance before and after each change, you can see which optimizations truly remove bottlenecks and which simply move the work around without real improvement. Python code profiling input performance. This material introduces a simple script for profiling tf.data input performance. Pause. It is designed for beginners and compares a slow data pipeline with an optimized one. Pause. The main goal is to measure how long it takes to process batches and to observe how well the computing device is being utilized. Pause. By focusing on these timing and utilization checks, learners can better understand and improve their input pipelines. This line is a command to install TensorFlow version 2.20.0, so the script uses the exact intended version of the library, which is important for compatibility and reproducible results. Because the line is commented out, it suggests that this installation step may be optional. It might already have been done in the environment, or left there as a reminder in case the correct version is not yet installed. We start by importing 3 standard libraries that support common programming tasks. The operating system library lets us work with files and environment variables. The time library allows us to measure how long operations take, which is useful for profiling performance. The random library generates random numbers and can be controlled with a seed so experiments can be repeated reliably. We begin by importing TensorFlow, since it is the main library used to build and train our machine learning models. Right after importing it, we check which TensorFlow version is installed. This step is important because different versions can have different features or compatibility issues. Knowing the exact version helps us make sure that our code will behave as expected and avoids problems when running or sharing the project. We begin by setting the random number generator to use a fixed seed, in this case, the number 7. This makes all later random operations produce the same sequence of results every time the code runs. Using a fixed seed is important for reproducibility, so experiments can be repeated and debugging becomes more reliable. We set TensorFlow's random seed to a fixed value, such as 7, so that any random operations it performs give the same results every time the code runs. This makes the behavior of the model predictable and repeatable. It is especially important for reproducing experiments and for debugging because it lets you reliably compare runs and track down issues. This line displays the version of TensorFlow currently in use. It provides a quick check that the correct version is installed and running. Confirming the version helps ensure compatibility and that TensorFlow's features and functions work as expected. This code uses TensorFlow's configuration tools to detect which physical devices, such as CPUs and GPUs, are available. Knowing the hardware that TensorFlow can access helps you understand the computing environment. This information is important for optimizing performance because it lets you see what resources can be used for running TensorFlow operations efficiently. This code uses TensorFlow to count how many physical devices, such as CPUs or GPUs, are available on the system. It checks the hardware configuration and then prints the total number of detected devices. This gives a quick overview of the computational resources that TensorFlow can use when running your programs. We begin by creating a small synthetic dataset specifically for profiling. We set the total number of examples to 2,000, which defines the size of this dataset. This size is chosen to provide enough data to meaningfully measure performance while still keeping it small enough for quick testing. As a result, we can efficiently iterate and refine our approach without being slowed down by a very large dataset. We create a tensor of integer identifiers that runs from 0 up to 2,000 using 32-bit integers. This tensor serves as the basis for a synthetic dataset. The dataset is then used to profile input performance and simulate how data would move through processing pipelines. This setup helps us test and analyze system behavior without relying on real data. This function simulates a computationally expensive preprocessing step on a tensor. It first converts the input to floating point format, so all later operations use floating point precision. Then it runs a loop 5 times, and in each iteration it adds 1 to the tensor and takes the square root. Repeating this transformation several times makes the function useful for testing and profiling performance in data pipelines. This function performs a simple, efficient preprocessing step on a tensor. It first converts the input to the float32 data type so that all later operations use floating point precision. Then it rescales the values by multiplying each element by 1/2 and adding 1, quickly adjusting the tensor's values with minimal computational cost. This function measures how long it takes to process a given number of batches from a dataset. It records the start time, then loops over the dataset for the specified number of batches, performing a simple sum on each batch to simulate work and counting how many batches were processed. After the loop, it records the end time and checks whether any batches were processed. If none were, it returns 0 to avoid dividing by 0. Otherwise, it computes and returns the average time per batch by dividing the total elapsed time by the number of processed batches. We begin by building a simple input pipeline using TensorFlow's Data API. We take our tensor of integer IDs and turn it into a dataset, which becomes the main structure for later processing and batching. By using the method that creates slices from the tensor, each integer ID becomes its own element in the dataset. This setup lets us efficiently apply transformations and operations to each data point in turn. This code uses TensorFlow's map operation to run a slow preprocessing function on each data element one after another. It does not use any parallel processing, so every item is handled sequentially. This design makes the data pipeline intentionally slow. The goal is to highlight how much performance can suffer when parallelism is not used in data preprocessing. The code takes the slow dataset and groups it into batches of 32 elements. This batching step is important because it helps manage memory more efficiently. By working with smaller, consistent chunks of data, the pipeline can process information more smoothly. As a result, the overall performance of the input pipeline is improved. The code configures the slow dataset to prefetch only one batch at a time. which means data preparation overlaps with model execution in a very limited way. This minimal prefetching is intentional and keeps the overlap between data loading and computation small. By doing so, it clearly exposes how much slower this simple pipeline is compared with a more optimized data pipeline that uses more aggressive prefetching. We begin by building an efficient data pipeline using TensorFlow's Data API. To do this, we create a dataset from a tensor slice of the integer identifiers, which initializes the dataset with the IDs we defined earlier. This approach organizes the data so it is ready for later transformations and performance optimizations. Using tensor slices also prepares the data to be processed in parallel, improving the overall efficiency of the pipeline. This code applies a fast preprocessing function to every element in the dataset using a mapping operation. TensorFlow runs this mapping in parallel and automatically tunes how the work is distributed. By using multiple CPU cores efficiently, this setup speeds up the data pipeline and improves overall performance. The code processes the optimized dataset in batches of 32 examples, matching the batch size used for the slower dataset. Using the same batch size keeps the conditions consistent across both data pipelines. This consistency is important because it allows a fair comparison of their performance and throughput. This code configures the dataset pipeline to prefetch data aggressively so that data loading overlaps with model execution. Prefetching keeps data ready in advance, which improves performance by reducing waiting time during training. It uses TensorFlow's automatic tuning to choose how many elements to prefetch based on system resources. This helps maximize throughput and minimize latency in the data input process. To reduce startup noise and get consistent performance measurements, we first warm up the slow dataset by taking its initial batch. We do this by iterating once over the dataset to fetch a single batch before we start timing. This simple warm-up step helps absorb any initial overhead so that the recorded performance better reflects steady-state behavior. To prepare the optimized dataset for performance measurement, we first warm it up by taking a single batch from it. We do this by creating an iterator over the dataset and retrieving the first batch. This simple step helps reduce initial overhead and startup time, so later performance measurements better reflect the true speed of the dataset, rather than one-time setup costs. We set the number of batches to 50 to measure how long our data pipelines take to process them. This fixed batch count lets us time the same amount of work for each pipeline configuration. By doing this, we can fairly compare the average processing time per batch across different pipeline setups. We measure how long it takes to process batches in the slow data pipeline by using a timing function that records the time needed to go through a set number of batches from the slow dataset. From this, we compute the average time per batch. This average latency per batch tells us how the slow preprocessing pipeline performs and helps us understand its overall efficiency. We measure how long it takes, on average, to process a batch in the optimized data pipeline. To do this, we use a timing function that records the time needed to iterate over a chosen number of batches from the optimized dataset. We then store this measured time so we can later compare it directly with the time from the slower pipeline. To find the throughput of the slow pipeline, we take 32 and divide it by the slow latency, which tells us how many examples are processed per second. If the slow latency is 0 or negative, we do not perform the division and instead set the throughput to 0 to avoid invalid calculations. To find the examples per second for the optimized pipeline, divide the batch size of 32 by the average latency of that pipeline. This result is the throughput, meaning how many examples are processed each second. However, You only perform this division when the latency is greater than 0. If the latency is 0 or not valid, you set the throughput to 0 to avoid a division by 0 error. This code reports how long, on average, it takes for a batch to move through the slow pipeline. It calculates the slow latency and then formats this value using a rounding function. The result is shown with 4 decimal places. This makes the printed summary both clear and precise for interpreting the pipeline's performance. This code reports the average time it takes to process a batch in the optimized data pipeline. It formats the latency value to 4 decimal places using a rounding function. This makes the timing result easier to read and to compare directly with the performance of the slower pipeline. This code reports how fast the slow data pipeline runs by printing its throughput in examples processed per second. It converts the computed throughput into an integer, so the output looks cleaner. The final value is then printed to the console, giving a quick view of the slow pipeline's performance. The code reports how many examples per second the optimized data pipeline can process. It converts the computed throughput value to an integer, so the printed result is cleaner and easier to read. This makes it simple to quickly inspect and compare the performance of the optimized pipeline with the slower one using a clear numeric metric. We build a simple neural network using the Keras sequential model, which lets us stack layers in order. The model takes input data with a single feature, then passes it to a dense layer with 8 units and a ReLU activation to capture nonlinear patterns. A final dense layer with 1 unit produces the output. This structure is a common choice for regression tasks where we predict a continuous value. The model is set up for training using the Atom optimizer, which is widely used because it is efficient and adapts well during learning. It uses mean squared error as the loss function, which is standard for regression tasks because it measures the average of the squared differences between predicted and actual values. Together, this configuration defines how the model updates its weights and how its performance is evaluated during training. We generate a label tensor by taking the first 2,000 elements from the original identifier tensor and converting this slice to the float32 data type. This conversion ensures that the labels have the data type the model expects during training. As a result, the labels integrate smoothly with the rest of the dataset and can be used directly in the training process. We build a TensorFlow dataset by combining feature and label tensors into pairs. Using the Data API, we efficiently handle large datasets while preparing them for training. The method that creates slices from tensors matches each element in the feature tensor with the corresponding element in the label tensor, effectively zipping them together. This results in a dataset where each entry is a feature and its label, ready for further processing and model training. We use TensorFlow's data mapping function to apply slow preprocessing only to the input features in the training dataset. A small function takes the features and labels, runs the expensive preprocessing step on the features, and leaves the labels unchanged. This setup lets us isolate and study how the costly preprocessing step impacts the performance of the input pipeline. The code prepares the slow training dataset by grouping it into batches of 32 examples, which makes training more efficient. After forming these batches, it uses prefetching with a small buffer so that data loading overlaps with model execution. This overlap reduces idle time and increases overall training throughput. We begin by applying a fast preprocessing step to the training dataset using a mapping operation that transforms each data point. In this operation, a small helper function takes the features and labels as inputs, but applies the fast preprocessing only to the features, leaving the labels unchanged. We also enable automatic tuning of the number of parallel processing threads, so the system can choose an efficient level of parallelism and speed up the preprocessing step by better using available resources. We begin by batching the optimized training dataset with a batch size of 32, which organizes the data into manageable chunks for processing. Then we prefetch the data using TensorFlow's automatic tuning, which chooses how many batches to load in advance. This overlaps data loading with model execution and makes input handling more efficient during training. We begin by noting the current time so we can measure how long training takes with the slow pipeline. The model is then trained on the slow dataset for a single pass, and training messages are turned off so no progress is printed. When training finishes, we record the time again and use the 2 timestamps to calculate the total duration of this training step. To measure how long training takes on the optimized pipeline, we first record the current time. We then train the model on the optimized dataset for a single epoch, with detailed output turned off. After training finishes, we record the time again. Comparing these 2 times gives us the total duration of the training process on the optimized pipeline. To find how long one epoch takes with the slow data pipeline, subtract the training start time from the end time. This difference is the total duration of that epoch. You can then use this measured time to compare the performance of the slow pipeline with the optimized pipeline. To find how long one epoch takes in the optimized training pipeline, we subtract the recorded start time from the end time. This calculation gives the total duration of a single epoch using the optimized dataset. We can then compare this duration directly with the time taken by the slower pipeline to evaluate performance improvements. This code reports how long training takes when using the slow preprocessing pipeline. It measures the duration of a single training epoch and prints that time in seconds. The value is rounded to 3 decimal places. This provides a clear, concise way to compare the training speed of the slow pipeline. This script compares a slow and an optimized TensorFlow data pipeline using a synthetic dataset of integer IDs. The slow pipeline uses a heavy preprocessing function, while the optimized one uses a lighter parallelized approach with auto-tuning for parallel calls and prefetching. It measures average time per batch and throughput in examples per second, showing that the optimized pipeline processes data much faster. A simple neural network is then trained on both pipelines, and the time for one training epoch is recorded. The results demonstrate that an efficient data pipeline not only speeds up data preprocessing, but also reduces overall model training time. Handling data order determinism. When optimizing an input pipeline, it is important to understand how data order and determinism influence performance and analysis. Deterministic pipelines keep data in a fixed order, which helps with reproducibility and debugging, but can limit parallel processing. Non-deterministic pipelines relax this strict ordering, allowing more flexible scheduling, higher throughput, and better resource use at the cost of small variations in data order. Recognizing this trade-off helps you distinguish performance issues caused by data ordering from those caused by computation. Performance bottlenecks often arise when a data pipeline forces a strict processing order. When reading many images, applying heavy augmentations, and batching them, one slow file read or complex transformation can stall everything, wasting GPU time and extending training. Allowing the system to process images in parallel and move forward with whichever ones finish first helps smooth out these delays. This is especially important with remote storage, where unpredictable latency can otherwise let the slowest file control the overall step time. When debugging a workflow, first decide whether you need deterministic ordering of data at each stage. Early in development, or when tracking down numerical issues, using a fixed data order makes runs easier to compare. Once the system is stable, you can relax determinism to increase parallelism and throughput. as long as training metrics remain consistent despite small changes in data order. In large-scale systems, it is common to use deterministic settings for debugging and non-deterministic settings in production, switching between them to balance performance and reliability while avoiding unnecessary bottlenecks. Python code, handling data order determinism. This script compares deterministic and non-deterministic data pipelines, highlighting how they differ in the order of elements they produce. It focuses on how the tf.data system can either preserve a fixed order or allow more flexible ordering. You are encouraged to run the cells to observe how the behavior changes and to see the printed element orders. The goal is to understand the trade-off between predictable ordering and potential performance gains. The line with the exclamation mark is a command to install TensorFlow version 2.20.0, which helps ensure the code runs with the expected behavior and compatibility, since different TensorFlow versions can behave differently. In this script, that line is commented out, meaning the installation step is optional, or TensorFlow is likely already installed in the environment. As a result, the code assumes the correct version is available without needing to run that command each time. The code starts by importing 3 common Python modules that support basic program functionality. It brings in the operating system module to work with files and environment settings, the time module to handle timing tasks like measuring how long code takes to run or adding delays, and the random module to generate random numbers and perform random operations. These imports prepare the program to interact with the system, manage time, and introduce randomness when needed. We begin by importing numerical and machine learning libraries such as NumPy and TensorFlow so we can perform efficient calculations and build models. We then set deterministic random seeds to control any randomness in our code. This makes our experiments reproducible, meaning the same code and data will produce the same results each time. Reproducibility is essential in machine learning and data processing for reliable analysis and easier debugging. This code prints the version of TensorFlow that is currently in use. Knowing the exact version helps you check that the correct library is installed for your project. It is important for compatibility with other tools, for reproducing results, and for debugging issues that may depend on the specific TensorFlow version. We begin by using TensorFlow's range function to create a simple sequence of integers. This sequence runs from 0 up to, but not including 8, increasing by 1 each time. It provides a straightforward and predictable set of values. We then use this sequence as the base dataset for the rest of the pipeline operations. This code defines a function that applies a slow mapping operation to input data and uses TensorFlow's function decorator to make it run more efficiently. Inside, it defines a small Python function that pauses briefly based on the input value, then returns the value squared as a 32-bit integer. This inner function is wrapped with TensorFlow's Py function so it can be used inside TensorFlow data pipelines. Finally, the code sets the output shape to match the input shape so TensorFlow can correctly process the results in later operations. There is a function called slow square that takes an input and computes its square in a deliberately slow way. Inside it, a helper function receives a value, waits for a short time that depends on that value, then returns the value squared as a 32-bit integer using a numerical library. The outer slow square function wraps this helper using a TensorFlow Python function so it can run inside a TensorFlow computation graph. It also explicitly sets the output shape so that the result has the same dimensions as the original input. This code uses TensorFlow's Py function wrapper to run a regular Python function, including a slow square operation with a sleep call inside a TensorFlow graph. The output type is set to a 32-bit integer, so it matches the expected data type in the pipeline. After wrapping, the code explicitly sets the output shape to be the same as the input shape, so TensorFlow keeps correct shape information. The function then returns the processed value, ready to be used in later steps of the computation. To build a deterministic dataset pipeline in TensorFlow, we first convert the base values into a dataset where each element is a slice of the original data. We then apply a mapping step that uses the slow square function in parallel, while setting the deterministic option to true, so the processing order is consistent across runs. After this transformation, we batch the elements into groups of 4 to improve efficiency. The result is a configured, deterministic dataset ready for further processing. We build a TensorFlow dataset by slicing the base values into individual elements. Then, apply a slow square function to each element using parallel processing. The processing order is set to be non-deterministic, so the element order may change between runs. After that, we group the processed elements into batches of 4 to make computation more efficient. The result is a configured dataset that is ready for further operations or analysis. This run-once function processes a dataset and measures how long the processing takes. It starts by recording the current time, then goes through each batch in the dataset, converts it to a NumPy array, and stores it in a list. After all batches are processed, it computes the total duration by comparing the current time with the start time. Finally, it prints the given label, the collected batches, and the elapsed time, rounded to 3 decimal places, allowing you to see both the order of the data and the performance of the processing step. This code demonstrates a deterministic data pipeline in TensorFlow. It creates a dataset from a fixed range of integers, applies a squaring operation to each element in a consistent order, and then groups the results into batches. The program measures how long it takes to iterate through these batches while converting them to NumPy arrays. Finally, it prints a label indicating the pipeline is deterministic, shows the order of the batches, and reports the total processing time, highlighting that the element order remains consistent across runs. We create a non-deterministic TensorFlow dataset by starting from a range of integers and applying a mapping function that squares each value, while allowing the processing order to vary. This is controlled by turning off deterministic behavior, so the order of elements in the output can change between runs. The squared values are then grouped into batches for more efficient processing. Finally, a helper routine iterates through the dataset once, collecting and printing each batch and measuring the total processing time, so we can observe how the non-deterministic execution affects both order and performance. The code runs the non-deterministic dataset pipeline a second time to show that the output order can change between executions. It recreates the dataset using parallel mapping with relaxed ordering, then passes it to a helper function that iterates through it. This helper collects and prints the batches while measuring how long the run takes. The label non-deterministic run2 is used to mark this specific execution and emphasize the variability in element order across runs. This script uses TensorFlow datasets to compare deterministic and non-deterministic data processing. It builds a simple dataset of integers and applies a slow squaring operation to simulate processing time. One pipeline processes the data in a fixed, repeatable order, while the other allows the processing order to vary between runs. As a result, the deterministic pipeline always produces the same batches in the same order, whereas the non-deterministic pipeline may output batches in different orders each time. The script also times both pipelines to show potential performance differences between these two approaches. In this lecture, you learn to optimize tf.data pipelines using caching, interleave, and parallelism settings for large datasets. Configure input pipelines that work efficiently with distributed training strategies. And diagnose and resolve common tf.data performance issues such as slow startup or CPU bottlenecks. In the next module, Module 6, we will go over computer vision. Thank you for your attention. See you all in the next lecture.